Hi all, today we discuss section 2.4 basis and dimension. To define basis, we first define spanning set. Spanning set. What is a spanning set? Once you consider R cross R or xy plane, if you are given any vector a comma b in R cross R, this is defined. This is denoted as R2. R2 is our xy plane. So once you fix a vector here, 1 0, and a vector here, this is 0 1, then you can express this AB as this can be written as this AB can be written as this much times the vector 1 0 and this much times vector 0 1. Okay, on the other way you can write this is A times 1 0 plus B times 0 1. Okay, so any vector in this R2 can be decomposed as a linear combination. It's a linear combination of these two vectors. That means a spanning set. So once you are given instead of this 1 0 and 0 1, if you are given 1 0 and 1 1, you can still write any AB in R2 can be written as some linear combination of these vectors. So x times or some c times 1 0 plus d times 1 1. This is also possible. Okay, so because you can easily evaluate this c and d in terms of a and b such that this a is equal to c times d and b is equal to d. Okay, so these two equations together imply that this d is equal to b. When you substitute b is equal to d is equal to b in this, you can get c is equal to a minus b. This shows that any a comma b can be written as this c is equal to a minus b. So this is a minus b times 1 0 plus b times 1 1. Okay, so this implies any AB can be written as a linear combination of 1 0 and 1 1 rather than this 0 or 1 0 and 0 1. So this shows that this set, these two sets have some interesting property. This set, any set which this set has a property that any arbitrary vector of R2 can be expressed by a linear combination of 1 0 and 0 1. Okay, so now we define a spanning set. Let V be a vector space and S is a subset of V is a spanning set of V if any vector, any U belongs to V is a or any U belongs to V is a linear combination of elements of S. Okay, this is the definition of a spanning set. Okay, so here 1 0 1 1 is a spanning set, and set 1 0 0 1 is also a spanning set. Okay, so these sets have these properties. In general, if you take any vector space V, you can define a spanning set in this manner. Now we have some examples. Determine whether any of the following sets are spanning sets of R2 considered as a column matrices. Okay, that means if we define R2 as column matrices, so any vector in R2 can be written in this form: xy, where x comma y belongs to R. Then we need to verify that these sets, which of these sets are spanning sets. So first we considered first one, A, that is already discussed in the previous session. That is any xy can be written as x times this 1 0 and y times 0 1. So this shows that S1 is a spanning set. S1 is a spanning set. Similarly, you consider B set S2. S2 consists of three vectors. Say E1 is equal to 1 0, E2 is equal to 0 1, and we have some other vector. This is some F1 is equal to 1 1. Okay, now we need to verify that this is a spanning set. So in order to verify this the set is a spanning set, we need to consider the arbitrary element of the vector space, and we have to write this arbitrary element as a linear combination of this. We already discussed this xy is decomposed into x times 1 0 plus y times 1 0 1. So you can write this as x times 1 0 plus y times 0 1, and we can incorporate this f1 by putting the coefficient is equal to 0. So this shows that even though there exists another vector in that set, still that set can span that v. Okay, that means any vector xy can be written as x times 1 0 plus y times 0 1 plus 0 times 1 1. So any vector xy can be expressed as a linear combination of these three vectors. Okay, this is a linear combination even though this coefficient is 0. So if this set spans, this S1 spans V or R2, we can say that S2 spans R2 as well, because S2 contains the vectors of S1. So it is enough to choose the vectors of S1 to span R2. Okay. So if we incorporate many more vectors to this set, you can still say that this S2 is a spanning set, because it is enough to choose E1 and E2 for spanning the vector space V. Okay, so this S2 is also a spanning set. S2 is a spanning set. That means S2 contains enough members of the vector space to span the vector space itself. Now we have C, the set F1 and F2. But F1 and F2 is not a spanning set, because when you consider, we need to say that any vector V, any vector of R2 can be expressed as a linear combination of this. But when you consider this 1 0, we can verify that is it possible to write this as some A times 1 1 plus B times 2 2. Okay, so if this happens, if you can find A and B such that A B satisfies this condition, you can say that this 1 0 0 1 0 can be expressed as a linear combination of this. But when you write this, you can say that A plus 2B is equal to 1 and B 2B is equal to 0. When you expand this or simplifying this, you can get this one. From this you can write B is equal to 0. When B equal to 0, you can get A is equal to 1. But this will be a contradiction, because when you put B equal to 0 and A equal to 1 in this expression, you can get 1 0 is same as 1 times 1 1 plus 0 times 2 2. This is a contradiction. So we can say that A equal to 0, B equal to 0, A equal to 1 are not possible for this expression. Okay, so we cannot get A and B such that this 1 0 equal to A times this plus B times this. This shows that this 1 0 cannot be written as a linear combination of these two vectors. So we say that this S3 is not a spanning set. Okay, so S3 is not a spanning set. So these are the examples.